talk about next is really the fundamentals of kinematics. So kinematics is basically if you are trying to model a manipulator, then given the angles, you need to figure out where, let's say, the hand is, so that if you know the position of the hand, you can use that in a manipulator setting to lift an object. Before that, we can talk about manipulators. We need to basically understand coordinate frames. How do you represent links when they're rotated and translated? So that's what we'll do first. Okay, let's talk about translation first. Okay, so the first part of the course, we're only doing 2D motion, and then we'll get to 3D. And I think it's kind of important to understand this well before we move on to 3D. So I'm just dividing into making it first 2D, then 3D. So that's like the frame which is fixed. So think of that frame as the ground frame. There's an x-axis, y-axis, and then when a body moves, it has its own frame, and that frame basically moves. So think of a body which is sitting right on the frame at the corner O, and then it moves. When it moves, in this case, translates. Let's say it goes to another location, and this is O1, X1, Y1. Okay, so what we're trying to do is understanding what happens to a point. Let's call it C. And this point could be some object, some point on that body. So I'm going to define a few distances. Say this is the X C distance, but in order to distinguish it from frame 1, which is the frame 0, which is represented by 0, and frame 1, which is represented by 1 here, I'm going to call that XC1. The frame number is always a superscript. And I'll take care of it when I have to do square, but for now, let's just stick to this where at the so superscript gives me the distance. That gives me the frame number, and this is YC1. Okay, then I'll call this distance as XO, YO. And intentionally, I did not put a frame number there because it's basically the distance between two frames. That is the origin of 2 frames. Now, the same point has a distance of XC in frame 0. So it's YC from frame along the y-axis of frame 0, and then XC in frame 0. Okay, so where we write positions is, let's say we want the location of point C in frame 0. Okay, so in this case, I would have to use XC and YC. So I can write it either as a vector, or I can just write in brackets, which I'll just show, XC, YC0, or I could write it as XC, YC. It's really, then the notation is not really important with this, that it is XC with a superscript 0 and YC with a superscript 0. So if you want to write the same position of point C in frame 1, so C1, it will be X, C1, Y, C1, or XC1, YC1. Okay, now we also have to somehow denote the position of frame 1, sorry, the origin O1. So remember, this origin has moved because the body has translated. But then it's not meaningful just to put O1. We need to always define it with respect to some frame. So in this case, the frame is frame 0. And you can see from the figure, it's just x0, y0. Right? You could also define the other way around, which is you could define the position of frame of the origin O with respect to frame 1. So compute the distance of this from here, and you'll see that it's nothing but minus x0, y0. Okay, so the main purpose of writing all this down is to just sort of agree on a notation. The notation is that the frame number always goes as a superscript, and then we use the index, the name, to be whatever point we're representing. So it was O1, O, C, which had ended frame 12. Okay, so that's translation. Let's look at rotations. Okay, so this is my ground frame, the world frame, which will be fixed. It's not going to move. And then assume that in this frame there is an object, and that object is instead of being translated, it's only rotated. So if it only rotates, it will maintain its origin to be the same as O, but it will be along a different direction. So I'm going to draw that, say, like so. And note that the origin doesn't change, so it's still O1. Okay, now we have the same same thing which you want to do, which is we want to represent a point on the body. Okay, the point, let's say point C. And so the way to find the distance is we drop perpendiculars to the axis. So we'll drop a perpendicular to, let's say, the x1 axis and the y1 axis. And this is my xc in frame 1, yc in frame 1. But I can also do the same thing with the other axis. See, so this is going to be x c in frame 0, y c in frame 0. Now we need to figure out what is the relation between xc, yc in frame 1 with xc, yc in frame 0. Okay, and this is probably some calculation you've seen before. It's basically using trigonometry, you can figure out what the distances are. So xc0 is, so you define this distance, then you basically so xc is also this distance. So you take the projection of this on the x-axis, that will be xc1 cosine theta. But then you got an extra piece here, which is this one, and then you have to subtract this piece, and that piece is basically is also theta. So it's yc1 minus yc1 sine theta. So that's something which I will not write in detail, but you can work it out. So it comes out to be xc0 cosine theta minus y, so xc1 yc1 sine of theta. Okay, so you can do the same thing for yc. That's going to be xc1 sine theta minus, sorry, plus yc1 sine theta. Okay, so we'll we'll exclusively deal with matrices. And so what we'll do is we'll write this as a matrix cosine theta minus sine theta, cosine theta, and a vector xc1, yc1. Okay, so this matrix is known as the rotation matrix. Okay, once you understand this, we never really do this trigonometry ever. We just use that rotation matrix to multiply with the position in frame 1 to get the position in frame 0. So we'll call this something. We'll call that R. This matrix is R1, 0. Okay, where this 1 indicates frame 1 and this 0 indicates frame 0. This is C0 because that's our that's the convention we've used. The C is the point and it's with respect to frame 0 and C1. So this rotation matrix tells you how you can relate the position or coordinates of point C1 with that of C0, and it has that form: cosine minus sine, sine cosine. Now, usually you are given C1 and you're told to find C0. What is C1? It's basically the coordinates in the local frame. And if you're confused with that, don't worry. We'll actually use this in an example where we are doing the kinematics of a simple two-link manipulator where it will become clear. We can also do the other way, which is going to figure out C1 given C0. All we need to do is multiply this expression with the inverse, right? So let's do that. So we have C0 is R10 C1. If you multiply it with the inverse, you know, this is I. And so we get C1 is R10 inverse C0. So if you take the inverse of R10, you'll see that it comes out to be cosine theta, sine theta, minus sine theta, cosine theta. But if you notice this expression and you compare it with, notice that the negative sign, there's a negative on the sign in row 2, column 1. But if you look at this one, there's a negative in row 1, column 2. So this R10 inverse is actually the transpose of that R. In fact, this is a property of all rotation matrices, that if you take it and multiply it with its transpose, you get the inverse. So this is also R10 transpose. So the property is of rotation matrices is that R10, or let's call it R. R times R transpose is identity. Hence, you see that R inverse is simply R transpose. So the advantage is that you replace a very complicated calculation, which is R inverse. If you know how to compute inverse, you need to do cofactors and adjoint and so on. You don't have to do that. You just take the transpose of the matrix and you have the inverse. Okay, so this is only rotations. We've not considered translations. The translation was figured out earlier. What we can do is we can actually combine the translation and rotation as one operation, and I'll do that next. So if you translate and rotate, then xc, yc0 equals x0, y0 plus cosine theta minus okay, so what's happening here is you start off in this frame. The second step is you translate. And the third step is you rotate. So we write this. This is the so step one and then step. So one way of writing this in a more compact form is to write it as C0, which is if you want to find the position of a point C in frame 0, what you need to do is you need to figure out where the origin of the frame is after translation. So that'll be O10, which is this O1, but in frame 0, plus the rotation matrix times C1. This is the same thing as what I wrote here. Okay, now this is just going from frame 0 to 1. If you want to go from frame 1 to 2, you do the same thing. C1 equals O to 1 plus 1 C2. And then you can just keep doing that. Cn equals On n plus 1 n plus so eventually what's happening is we want to relate everything with respect to the world frame. So this is like the world frame, or I'll call it world frame because it's fixed, it's not going to move. If you imagine that one corner is the world frame, and if there's an object which is moving, it first goes to frame 1. Okay, so it translates, it rotates, then it moves somewhere else, it translates, rotates, keeps doing that. So when it keeps doing these transformations to go from point 1 to point B in several steps, n steps, you're really interested in knowing where it ends up in n step with respect to the world frame. And so what you need to do now is sort of combine all these equations as one. So what you'll do is you'll sub this value here. The C1 will go there, and then the C2, which will be here, will go there, and then you'll get one expression relating Cn with C0. I'll write that expression down. So this is the combining all the equations together. C0 is O10 plus R10 So this part is the translation part. You can only see that there's O1, 0, O2, 1, and so on. And then there's a part corresponding to the rotations. Okay, so I think that's a very complicated expression to remember or even to code. It turns out there's a simpler way of representing this complicated expression. It's known as a homogeneous matrix. So let me first put some notes here. This is the translation piece. This is the rotation piece. and it's clearly cumbersome to remember and write. So the solution is what is known as a homogeneous matrix. So we'll define a homogeneous matrix, or homogeneous transformation as it is called. It's denoted by H, and that homogeneous transformation actually captures in the rotation and transition using one matrix. So the homogeneous matrix is this H equals R. So just like we have successive frames defined by R's, so R1 with respect to R0 with respect to frame 1 and so on. This is just relating one frame with the other frame, the previous frame, Ri, I minus 1, 0, and 1. Okay, now, this notation might be confusing. It's like there's a matrix there, but the matrix has matrices inside it. So it's actually, let me put the dimensions here. This is a 3 by, in this case, it's a 2 by 2 matrix, just one which I wrote down earlier. Cosine, sine, and so on. O1, O, remember that is the origin. It's x0, y0, so it's 2 cross 1. This 0 is 1 cross 2, so 1 row, 2 columns, and then this 1 is 1 cross 1. So if you combine this whole thing and you look at the rows and columns of this entire matrix, you see that this H is 3 cross 3. Okay, I'm not sure if you've been used to this, but this is what is known as a block matrix. That is a matrix consisting of set of matrices which you can put in the right. They need to have the right dimensions so that it actually is consistent. Okay, so how does this make our life easy? Remember, this is a replacement for using this notation. It turns out that you can actually write C I minus 1 as H I minus 1, sorry, H I minus 1 C I. So this is, so as is the same as C I minus 1 equals so that expression down there, this one which we are trying to represent is actually written as that. So we can check that. What we'll do is expand this out. So I'm going to take this, write it down. Okay, now something I want to tell you is this C is actually slightly different from the C over here in the following way. It's the same as this C. So let me actually put a different symbol for it. Let's just make it a capital C so that it's different. This is small c and I just made it bold-faced as opposed to this C. And the way it's different is this is small, this capital C is the small c, and here there will be a 1. So capital C is small c, which is this. You know what? Let me just change the color. Zero. It should be I minus 1. The same thing here. It will be C I 1. So when you expand this out, you'll see that it is equal to EI plus OI I minus 1. So what I did was I took this, multiplied with C. So I got the first term, and then I multiplied the second term with 1, and I got this. And then the second, for the second row in the block matrix, it will be 0 times C, which will be 0, and 1 times 1, which is 1. So you see that the first term, the first line in this. Okay, the first line, which is this, is the same as this. It's exactly the same. And the second one this is basically a 1. It's 0 plus 1 is 1. And the second one is, let's say, 1, the same as this. And you can really discard it. It really is saying that 1 is 1, which is true. So once you write it this way, now you have one matrix. And if you want to write a complicated expression like this, it turns out that you can write it very efficiently in one line as follows. So you'll say, the boldface C0 is H10, H21, H32, so on, Hn minus 1, Cn. Okay, so that basically is the expression which I wrote down. So what we'll do is we'll never really write this expression. We will not write it. We'll only write this one because it's so easy to manage. It just has these H's, and you should remember what H is. H is basically that matrix. So what I do normally is I write a function for this H, and I just keep calling it whenever I need it. I just put them together, and I'll show you code where you can very easily get that.